Hi, so for today we're going to talk about thermal physics. So thermal physics is actually a very broad study and it is the introductory subject for thermodynamics. Okay, by the way, what is thermal physics? Thermal physics is the branch of physics that deals with the study of temperature, heat energy, and their relation to matter. So in our everyday life, we are dealing with this kind of subject. Oh, well, of course, just right now, it's summertime. We say that the temperature is high and we say that it's hot. Our body feels hot because the temperature is high. And when it comes to heat energy, application of heat, such as when we are cooking something, okay, we apply heat in order for us to cook something, okay, or when we are about to take a shower, we are actually having a cold shower or hot shower. Well, basically that's the application of or some of the everyday dealing we have for heat. And basically when we talk about temperature, temperature is defined as the hotness or coldness of a body. So in other words, when we say that an object has a high temperature, well, it's hot. Basically, it's hot when we touched it. Okay, and heat is, in other words, or in other definition, in contrast with temperature, heat is not the same with temperature. Heat is actually a form of energy that flows from the high temperature to a low temperature. Okay? So in thermal physics, when objects are heated or cooled, the temperature changes, well, of course, and some properties of the materials change. Okay? So there is a property of a material that is changing variably because of the temperature applied on that object. And those properties are what we call the thermometric properties, which is any physical property that changes measurably with temperature. Basically, the basic idea is that if we apply heat to an object, okay, a high temperature will expose an object to a high temperature, the tendency is that it turns out that it expands. While if we're going to cool that object, the tendency is that the object shrinks. Okay? So, temperature, as I've said a while ago, is the degree of hotness of an object and it can be measured by what we call the thermometer. Well, actually, thermometer is not new to us because it's the instrument that our mother or father use whenever we have a fever to measure our body's temperature. So, temperature is usually expressed in Celsius, Fahrenheit, or even in Kelvin scale. Okay, so later on we're going to talk about how are we going to convert Celsius to Fahrenheit and Fahrenheit to Celsius, or from Celsius to Kelvin. Okay, so in other words, another definition here is we have the heat. Heat is actually the energy which travels from high temperature to low temperature in a matter. It's an energy. Therefore, its units must be joules in terms of SI unit. It is also called the thermal or the internal energy. So, one example of that is that if you are inside in an air-conditioned room and your friend actually left the door open, you say the aircon will actually the cool or the cool air from the aircon will go outside, please close the door. Okay, well, that's not actually true. Based on our definition of heat, it's actually the energy which travels from high temperature to low temperature. So might as well you say to your friend, please close the door. Why? Because the heat outside will come inside our room. So basically, from high temperature, which is outside of your air conditioned room, going inside the air conditioned room. From high temperature outside to low temperature inside. That is the flow of heat. Okay, so we have here the conversion of Celsius to Fahrenheit and the conversion of Fahrenheit to Celsius. So we have this formula, T sub F is equal to temperature in Fahrenheit is equal to 9/5 of temperature in degrees Celsius plus 32 degrees. Okay? And if we're going to convert Fahrenheit to Celsius, So we have T sub C, which is the temperature in Celsius, that is equal to 5/9 of TF, the temperature in Fahrenheit, minus 32 degrees. So I will not be having any example in this because it's quite easy. Okay, but there is something that I would like to share with you, that there is another what we call the Kelvin scale, denoted by big letter K, and its formula is actually the degree Celsius, the temperature in this degree Celsius plus 273. So, what if we're going to find the temperature in Kelvin, given that our temperature in Celsius, degrees Celsius, is actually 20 degrees? What is the temperature in Kelvin? So simply, by our formula, the temperature in Kelvin is degrees Celsius plus 273. So that is 20 degrees plus 273. That is 293 Kelvin. Okay? So that is our conversion from Celsius to Kelvin. Okay, and we have another what we call the denoted by big letter R, and that basically is what we call the Rankine. Okay, Rankine, another form of another unit for uh, temperature, Rankine. So it's basically R is equals to degree Fahrenheit plus 460. So, for example, we have a temperature that is in degree Fahrenheit, or Fahrenheit, simply Fahrenheit, as 30 degrees. Okay? So, the conversion from Fahrenheit to Rankine is 30 plus 460, and that is basically 490 degree Rankine. Okay? This is another unit for temperature. Going back to our discussion, so you can easily also solve this conversion of temperature in your calculator, in your Casio calculator, if I'm not mistaken, shift constant or shift convert 38, 37, okay? Converting Celsius to Fahrenheit. Anyway, so mercury, let's take a look at the thermometer and the object inside the thermometer, which is the mercury. So mercury is a common liquid element used in thermometer. Well, basically mercury is the only metal in the form of liquid. Okay, it freezes at negative 39 degrees Celsius and boils at 357 degrees Celsius. So the basic concept of the thermometer is that we have here the basic construction of thermometer, and inside the thermometer we have here the metal mercury, the only metal liquid in the periodic element. Okay, so it what happens here is that if this thermometer is used to measure your body temperature, it's basically put in your armpit. Okay, so to measure your body temperature, for example, you run a fever and your temperature of your body goes up, so your mother or the doctor or the nurse will actually try to measure your temperature by placing a thermometer in your armpit. Okay? So what happens is that in your armpit, in our armpit, it produces heat. It produces the temperature or the heat that we have in our body. So what happens is that this mercury tends to expand. Why? Because this mercury is being heated. And when we say that this, if an object is being heated or is subjected to a high temperature, the tendency is that it expands. So it will expand in this measuring scale of our thermometer, so that what happens is that if it is taken outside, or what do you call that, if it is removed from your armpit, from our armpit, to see if what is our temperature, it turns out that most commonly, if you have a fever, your temperature will be in this. So that the mercury, as long as it is heated or applied to a heat subjected to a high temperature, it would actually expand and expand and expand and expand. Why? Because that is a property of a metal, thermometric property. Okay? Is that when the mercury is heated, it turns out that it expands. Well, again, after some time, after letting it out of your armpit, okay, what happens is that the mercury turns out to what? Shrink again. because the temperature in the room where you are being examined by the doctor or the nurse is not actually the same with the temperature in your armpit or with your body temperature. So it shrinks again. It is being exposed to a lower temperature so that the mercury, what happens is that it turns or it goes back into this. Why? Because if the body is heated, it expands, but if the body is subjected to a low temperature or cooled, it shrinks. Okay, that's the important property of our objects, okay, materials, thermometric properties. So all matters expand when heated because of the increase in the vibration of the molecules. Well, actually, that is a microscopic definition. When we increase the heat, the vibration of the molecules in the body is increasing, thereby producing heat. Okay, so and what happens? We have here an image of the railway of the train. So on the left side, this is a good example of a railway that has a gap in between, and this is actually a bad representation or a bad design of a railway. So the railways of trains have spacing because they expand during summer or whenever the temperature is high. So in our left image, okay, we have two metal bars as a railway. So what happens is when this is exposed to a very high temperature, the tendency is that it expands. Okay? And they have a gap in between so that they would never actually have a problem of being bent. Why? Because our temperature is changing. Well, of course, imagine if it's summer, then these metal bars will expand. If come winter, for example, we are in countries that have four seasons, well, this metal will shrink. Okay, and that shrinking and expanding of the material, if there are no gaps in between, would actually result into this twisted railway. So what happens is that whenever we don't have a gaps in between like this, so this railway would actually experience of what we call a stress, thermal stress, because of the continuous expanding and shrinking and expanding and shrinking. Thus, because this railway has nowhere to go, the tendency is that it would be twisted because of the expansion of the metal. If there are no spacing between this metal. So I would not ride a train that has a railway like this because most probably that train will go out of track when the train actually passes through this track. Okay. So, what is the zeroth law of thermodynamics? Basically, if you have three bodies, body A, body B, and body C, if C is initially in thermal equilibrium with both both A and B, then A and B are also thermal equilibrium with each other. So we have a system A and B. If A and B are in thermal equilibrium, for example, we have two things, okay, with two objects, we actually put them together. So what happens is that after some time, these two objects will have the same temperature. Okay? So for example, we have two systems that are in thermal equilibrium if and only if they have the same temperature. So for example, we have a hot object here and we have a cold object here. Okay? We put them together. Okay, so what happens after some time, there will be a heat transfer from the hot object to the cold object. Or in other words also, after some time, their temperature must be equal. Okay, so to further illustrate that, let me just have a drawing. For example, you have here, uh, you have a cup of water. Okay, you have a cup of water here. And this water is actually has a temperature of, let's say, that's a cold water. So let's say that the temperature of the cold water is 15 degrees Celsius. and you're going to drink coffee, so that what are you going to do is you have another one here, you have a pitcher here, okay, that is basically have a hot water, boiling water, let's say 100 degrees Celsius, okay. So you're going to put that hot water in here. So the tendency is that what will happen is that here is your cup again. So what happened is that you mixed a 100 degrees Celsius hot water with a 15 degrees Celsius of cold water. So after some time, some point in time, what will happen? The temperature of this water should be what? Let's label that as X. Should be less than 100 degrees Celsius, and it must be greater than 15 degrees Celsius. Considering that there is no outside energy or temperature affecting this cup of water, okay, for your coffee. So, what happens here is that, let's say after mixing, that the value of the temperature of that water inside your cup will be, let's say, let's meet it, 20 or, oh, my mistake. So this is only ideal, or this is only an example. So let's say that would be 35, 36 degrees Celsius. The fact is, when you measure the temperature here, it's 36 degrees Celsius. And the fact also, if you measure the temperature here on the bottom of your cup, it's also 36 degrees Celsius. So, in any point of this water at any height, or any height with respect to this to the bottom of the cup, well, the temperature is the same. That is basically a thermal equilibrium. Okay? If and only if the two objects have the same temperature. And after some time, also, the temperature of the cup will be 36 degrees Celsius. Okay, and after some time, you leave it there, just leave it there. The temperature of that water inside, the temperature of that cup, is the same as the temperature of the surroundings. Okay, because there is a heat gain and heat loss. Okay, energy exchange between the environments and the objects. Okay, so that is the zero law of thermodynamics. So we have here the thermal expansion. So a rod of material that has a length of, let's say, L naught, that is the initial length, at some initial temperature T sub 0, when the temperature changes by delta T. Okay, when we increase the temperature experienced by this rod, the length changes also by a certain length, delta L. And what are we going to do is that if we increase again twice the change in temperature, the change in length, delta L, will also increase. In other words, the increase or the change in temperature is always directly proportional to the change in length. Okay? So here is our formula for thermal expansion. So delta L, we have here the delta L is equal to the alpha L sub 0 L or L naught delta T, wherein delta L is actually the change in length of the material, and L naught is actually the initial length of the material. Delta T is actually the change in temperature. In other words, we can replace this as uh, final temperature minus initial temperature, and we have here the alpha, which is the coefficient of linear expansion. The coefficient of linear expansion is different for every material. This is the constant that we have in our equation, thermal expansion. Okay, so what are we going to do here? So this delta L is actually what? Is actually the change in length. That is the change in length. So again, if we have a rod here, let me just draw it. Okay, if we have a rod here, okay, this changes by this certain amount if we expose that to heat. So this change is actually what? The delta L. The whole length at which this rod changes is what we call L. So if we wish to measure the total length after this metal rod is being exposed to a high temperature, we have to find L, and that is L. This is our initial length before we expose this into high temperature. So L is basically L naught plus the delta L. So what are we going to do is that L naught, the initial length, plus delta L is equal to alpha L naught delta T. So we can factor out L naught so that we have 1 plus coefficient of linear expansion or thermal expansion delta T. So this is now the total length. So don't be confused with the change in length and with the total length. So we have here in our PowerPoint, so we have here the following formula. So this is the final length, the total length at which the object expands. And delta L is the change only in length. How much length it increased. That is the meaning of delta L. So when an object undergoes thermal expansions, any holes in the object expand as well. Just as like if we have here a plate, okay, when this plate is actually heated, okay, the dimensions increases. But when we punch a hole inside this plate, okay, such that this is our hole, what happens is if that this is exposed to a high temperature, the hole also expands. Not only the dimensions, but also the hole. Because all of the dimensions should expand. Okay? So the common misconception is that this expands. But actually, the hole also inside the plate must expand too. So, okay. So here are some coefficients of some linear expansion of some materials. So we have here the aluminum, the brass, and bronze. But the most common here is the steel. Okay. And by the way, the unit of the coefficient of linear expansion is actually in terms of alpha. Let's say some term of constant over degrees Celsius. So it can be, let's say, just for the coefficient of linear expansion of steel. A while ago, we have seen that. So that is 11 times 10 raised to negative 6 per degree Celsius. Okay, that's the unit of our coefficient of linear expansion. Okay, so we have here also the average volume expansion coefficient. So if we have the coefficient of linear expansion, also if we are increasing the temperature, it also causes an increase in volume for both solid and liquid materials, such that if we have delta V, the change in volume is equals to beta V naught and delta T multiplied by delta T. What is this delta V again? The change in volume when the object is heated, and that is equal to the coefficient of volume expansion. That's the meaning of beta. And V naught is actually the initial volume of the material. Delta T is actually the change again in temperature. Now, there is a significant relationship between the coefficient of linear expansion and the coefficient of volume expansion. Whereas the coefficient of volume expansion beta is always equal to the thrice the coefficient of linear expansion of any material. So here are some coefficients of volume expansion of some materials. So we'll be using them later. So, sir, do I have to memorize all of that? No, it's actually given mostly given in your exam or in your quizzes. So, but for board exam, such as the coefficient of linear expansion of steel, you must memorize it. Okay? So, let's have an example here. I have copy pasted this. So, we have here that question. Oops, I'm sorry. So, for number 1, a surveyor uses a steel measuring tape that is exactly 50 meters long at a temperature 20 degrees Celsius. The markings on the tape are calibrated for this temperature. Letter A, What is the length of the tape when the temperature is 35 degrees Celsius? So what is the length of the tape? Are we being asked of delta L or DL? Well, of course, what is the length? That means the total length. Okay, after the steel measuring tape is exposed to a high temperature. So our formula here is L naught plus coefficient of 1 plus, my mistake, okay, 1 plus, well, I'm so sorry, our formula should be, again, what? Let's derive first. L naught plus the delta L, of which our L naught is, or delta L is equal to coefficient of linear expansion, L naught delta T. Okay? So L is actually L naught, factoring L naught, 1 plus alpha delta T. So this will be our formula that we're going to use to solve this problem. So again, the initial length is given, that is 50 meters. 1 plus the coefficient of linear expansion for what? For steel. And that is basically given. So 11 times 10 raised to negative 6 per degree Celsius. Multiply it by the final temperature is that 35 degrees Celsius minus the initial temperature, which is 20 degrees Celsius. And if we're going to compute that, so we shall arrive at an answer 50, say 50 plus 1 times 1 times 11 times 10 raised to negative 6, 35 minus 20. So we have 50.008. So the length from 50 meters became 50.008 meters. So that is a very small amount of expansion. But technically, if you're having if you're very strict with the length, this might be critical. Okay, from 50 it became 50.008 meters after a change in temperature of 15 degrees, because 35 minus 20 is 15. So letter B, when it is 35 degrees Celsius, the surveyor uses the tape to measure at a distance. The value that she reads off the tape is 35.794 meters. Well, assuming that the user did not actually notice that there is a change in length, so what are we going to do is the actual distance is basically what? Basically L over L naught multiplied by the 35.794 measured value. Okay? The ratio. So L is actually 50.008 meters divided by 50 meters times 35.794 meters. So we have 50.008 over 50, 35.794. That is 35, 35.8 meters. Okay, so for our next problem, we have volume expansion. So I copy paste it here. So we have a 200 cubic centimeter glass flask is filled to the brim with mercury at 20 degrees Celsius. So we can write the given. We have here the initial volume V naught is 200 cubic centimeter, and we have the initial temperature TI 20 degrees Celsius. So how much mercury overflows when the temperature of the system is raised to 100 degrees Celsius? TF is 100 degrees Celsius. The coefficient of linear expansion of the glass is, okay, we have the coefficient of linear expansion, that is 0.4 times 10 raised to negative 5 Kelvin raised to negative 1, or per Kelvin. Okay, so that is coefficient of linear expansion. What we are after is the coefficient of volume expansion, because remember in our formula, delta V is actually beta B naught delta T. And the given is the coefficient of linear expansion of the glass, which is this. But we can actually find the beta or the coefficient of volume expansion of the glass, B glass, beta glass, by multiplying it by 3 of the coefficient of the linear expansion of glass. So we have 3 times 0.4, that is 1.2 times 10 raised to negative 5 per Kelvin. That is now the beta for the glass. And the given here, my mistake, is not the coefficient of linear expansion of mercury, but rather this is already the coefficient of volume of mercury. So the beta of mercury, again, I have like correction in that question. So that is 18 times 10 raised to negative 5 per Kelvin. And what are we going to do? To measure the mercury that overflows is that what happens is that if we imagine the glass is filled with mercury, so when glass is heated, its volume expands. Also, the mercury in it also expands. So, because the mercury is a metal, the tendency is that the volume of mercury is much more, or the expansion of mercury is much greater than the expansion of glass plus, the volume expansion of the both. So what happens is that in order for us to get the volume of the spilled or yung overflowed mercury, is that we have to what? Subtract the delta V of the mercury minus the delta V of the glass. So, in order for us to get that, we have the beta of mercury. What is the beta of mercury? That is 18 times 10 raised to negative 5. Okay? So, Kelvin, multiplied it by what? The volume of the mercury, which is 200 cubic centimeters. Then the delta T is 100 degrees Celsius minus 20 degrees Celsius. That is 80 degrees Celsius minus the beta of the glass, that is 1.2 times 10 raised to negative 5 per Kelvin, multiplied also by the 200 cubic centimeter, okay, of the volume of the glass. They have the same volume. And multiplied also by, well, of course, 80 degrees Celsius. And if we're going to calculate what is the volume spilled, okay, that is basically in one decimal place is 2.7 cubic centimeter. Okay? Sir, I have a wonderful question here, sir. Why did not we change or convert first this temperature in Celsius into Kelvin, or convert this Kelvin into degrees Celsius so that we can cancel the units? Well, actually, that's the magical thing about the thermal physics. Because the change in temperature in Celsius is also the same as the change in temperature in Kelvin. So that's the magical thing, that you need not to convert this into Kelvin in order for you to get the correct answer. Because if you convert this into Kelvin, then basically the answer would be the same. Okay? So yeah, that's the thing. So there's no problem with that in terms of Celsius and Kelvin. Okay? So the quantity of heat energy transfer takes place solely because of temperature difference is called the heat flow or the heat transfer, and energy transfer in this way is called heat. Okay? So later we will continue this study all about heat. And that's it for now. Thank you so much for listening, and God bless.